imagine looking down at the Earth from very high above. Before we go any further, if you want a brand new Earth topic every single night to fall asleep to, subscribe. One tap and a new story is waiting for you every evening. From that great height, you would see something remarkable. Stretching across the very top of the world, like a wide green crown, sits the largest forest on Earth. This is the Boreal Forest. It wraps around the entire northern part of our planet. It covers parts of Canada, Russia, Scandinavia, and Alaska in one vast, unbroken sweep of trees. From space, it looks like a dark green band drawn just below the Arctic, running from one side of the globe to the other. The scale of it is hard to hold in your mind. The Boreal Forest covers roughly 11 million square miles of land. That is about 30% of all the forest on Earth. It is larger than the Amazon rainforest. It is larger than the continental United States and Canada combined. It is simply one of the biggest living things our planet has ever grown. Scientists call it by another name too. They call it the taiga, a Russian word that has been used for centuries by people living near its edges. The word taiga carries the feeling of something ancient and immense, something that does not need a human name to know what it is. From above, the forest looks dense and still. But look closer, and you begin to see the details. The trees are mostly dark. Spruce and fir and pine, with their narrow pointed tops, stand close together in long rows. Between them, you can spot pale patches of birch and aspen, their white bark catching the light like small candles in a dim room. And threading through all of it, you can see the silver glint of rivers and the dark mirrors of countless lakes. The Boreal Forest holds more fresh water than almost any other place on land. It is home to millions of lakes, ponds, rivers, and wetlands. Canada alone holds about 25% of the world's fresh surface water, and much of that water sits inside or flows through the boreal. The forest holds it, filters it, and slowly releases it into rivers that run to the sea. Now think about the quiet. Standing inside this forest, the sound changes. The wind moves through the needles of the spruce trees in a low, soft hiss. The ground underfoot is thick with moss, and moss swallows sound the way, a heavy blanket swallows light. In winter, the snow piles deep between the trunks, and the silence becomes something you can almost feel pressing against your ears. The Boreal Forest sits in a band between roughly 50 and 70 degrees north latitude. That means it lives in a zone where winters are long and brutal, and summers are short and bright. The sun barely rises in winter. In summer, it barely sets. The forest has learned to live inside these extremes, and it has been doing so for a very long time. After the last great ice age ended, roughly 10,000 years ago, the glaciers pulled back and left bare scraped ground behind them. Trees moved in slowly, following the warming soil northward. The Boreal Forest we see today is still young in geological terms. It is still settling into the land the ice left behind, and yet it feels ancient. Walking through it, you sense that it has its own rules, its own rhythms. The trees do not grow tall and wide the way tropical trees do. They grow narrow and pointed, shaped by the weight of heavy snow that would snap a broad branch. Every shape in this forest is an answer to a question the climate asked. The Boreal Forest also holds an enormous amount of carbon. Carbon is the element that plants pull from the air and store in their wood, their roots, and the soil beneath them. The boreal stores more carbon than any other land-based ecosystem on Earth. Scientists estimate it holds about 30 to 40% of all the carbon stored on land. It is one of the great quiet forces keeping our atmosphere in balance. All of this, and most people will never see it. It sits far from cities, far from roads, far from the noise of ordinary life. It simply exists, enormous and patient, doing its work in the cold and the dark and the long green summers. It breathes for the planet. It holds the water. It shelters the animals. And tonight, as you rest, it is out there still, standing in the dark beneath a sky full of stars. The Boreal Forest did not appear overnight. It took thousands of years to become what it is today. To understand it, you have to go back to a time when much of the northern world was buried under ice. About 20,000 years ago, enormous sheets of ice covered vast stretches of North America, Europe, Asia. These glaciers were not thin layers of frost. They were walls of ice, sometimes more than a mile thick. They crushed everything beneath them. They scraped the land bare. Where forests once stood, there was nothing but frozen silence. Then, slowly, the climate began to warm. The ice started to melt. It retreated north over thousands of years, pulling back like a slow tide. And in the wet, cold ground it left behind, life began again. Grasses came first, then shrubs. Then, little by little, the trees moved in. The trees that colonized this cold, raw land were tough ones. Spruce and fir and pine and larch. They were built for cold. They were built for poor soil. They spread north as the ice retreated, following the edge of the warming land. By about 10,000 years ago, something recognizable as the Boreal Forest had taken shape. It was young in geological terms, but it was already vast. Today, the Boreal Forest stretches in a wide band across the top of the world. It runs through Canada, Alaska, Russia, Scandinavia, and parts of northern China. Scientists sometimes call it by its Russian name, the taiga, which simply means forest in that language. It wraps around the globe like a green ring just below the Arctic. If you could look down at Earth from far above, you would see it clearly. A dark, dense belt of green and gray, enormous and unbroken. The numbers are hard to hold in your mind. The Boreal Forest covers roughly 6 million square miles. That is about 3% of the entire surface of the Earth. To put that in terms that feel real, the United States covers about 3.5 million square miles. The Boreal Forest is nearly twice that size. It is the largest land-based ecosystem on the planet. Nothing else on land comes close. Canada alone holds about 1/3 of the world's boreal forest. That is roughly 1.5 million square miles of trees, wetlands, rivers, and lakes. Most of it untouched by roads or cities. Russia holds even more. Its boreal stretches for thousands of miles across Siberia, a word that itself has become a kind of shorthand for cold and remote and wild. The forest sits between two other great zones of the earth. To the south, it gives way to temperate forests and grasslands. where winters are milder and the soil is richer. To the north, it fades into the tundra, that open, treeless plain where the ground is frozen year-round, and even the hardiest trees cannot survive. The boreal lives in the space between those two worlds. It is the last great forest before the ice. The soil beneath the boreal is not like the deep, dark soil of a farm. It is thin and acidic. The cold slows down the breakdown of dead leaves and wood, so nutrients build up slowly. In some places, the soil is only a few inches deep before you hit rock or frozen ground. Trees here do not grow fast. A spruce tree in the boreal might be 60 years old and still only as tall as a person. The cold simply does not allow for speed. And yet, despite the thin soil and the brutal winters, the forest thrives. It has been doing so for thousands of years. The trees are patient in a way that is hard to imagine. They grow a little each summer. They rest through the winter. They hold their ground. The age of the forest itself is worth sitting with for a moment. 10,000 years sounds ancient to us, but in the long story of the earth, it is recent. The dinosaurs vanished 66 million years ago. The Rocky Mountains began forming over 70 million years ago. The Boreal Forest, by comparison, is a newcomer. It grew up in the quiet aftermath of the last great ice age, filling the space the glaciers left behind. It is a forest built on the memory of ice. Everything about it, its trees, its soil, its animals, its climate, reflects that origin. The cold shaped it. The ice made it possible. And the slow warming of the world gave it room to grow. It is a forest that carries its history in every branch and every frozen root. The winter is where the boreal forest begins, not just in the calendar sense, with the first snow falling in October and the last frost lingering into May, but in a deeper sense. The boreal forest exists because of winter. It was shaped by cold the way a river shapes a canyon, slowly, completely, over a very long time. To understand the forest, you have to understand what the winter actually feels like here, in the heart of the boreal, in places like central Siberia or northern Canada. Temperatures can fall to minus 40 degrees. That number is the same in both Fahrenheit and Celsius. At that point, the two scales meet, and the cold becomes something beyond ordinary description. Exposed skin freezes in minutes. Diesel fuel thickens and stops flowing. The trees themselves crack and pop in the night, the sound carrying far through the still air like a distant gunshot. The winter in the Boreal lasts a long time. In many parts of the forest, snow covers the ground for 6 to 8 months of the year. That is more than half a life spent under snow. The sun, when it appears at all in the depths of December, stays low on the horizon. It rises late and sets early. Some days bring only a few hours of pale gray light before the darkness returns. The forest sits quietly under all of it, waiting. And yet the snow is not the enemy. The snow is a gift. It acts as a blanket, a thick layer of insulation that traps a small amount of warmth just above the ground. Beneath a deep snowpack, the soil temperature stays far warmer than the air above. Small mammals like voles and shrews live their entire winters in this hidden space, moving through tunnels between the soil and the snow's surface, sheltered from the killing cold above. The snow makes their survival possible. Without it, they would freeze. Without them, the predators that hunt them would go hungry. The whole web of winter life depends on snow doing its quiet work. The cold shapes the trees in ways you can see just by looking at them. Spruce and fir trees, the most common trees in the Boreal, grow in a narrow cone shape. That shape is not an accident. It allows heavy snow to slide off the branches rather than pile up and break them. The branches themselves are flexible, bending under weight rather than snapping. Even the needles, thin and waxy and dark green, are built for winter. They hold their color all year, which means the tree can begin making food from sunlight the moment the light returns in spring, without waiting to grow new leaves. Every feature of these trees is an answer to the same question. How do you survive a winter that never fully lets go? The cold also slows the process of decay. When a tree falls in the Boreal Forest, it does not rot quickly the way it might in a warm rainforest. The bacteria and fungi that break down dead wood work slowly in the cold. A fallen log might take decades to fully fully return to the soil. This means the forest floor holds onto its carbon for a very long time. The dead wood, the fallen leaves, the thick mat of moss, all of it stores carbon that would otherwise escape into the air. Scientists estimate the Boreal Forest holds roughly 30% of all the carbon stored on land in the world. The cold is the reason. The cold slows everything down, including the release of that stored carbon. There is something almost meditative about the boreal winter. The forest does not fight the cold. It does not resist it. It simply adjusts. The trees pull their energy inward. The animals find their strategies, some migrating, some hibernating, some simply enduring. The whole forest enters a kind of deep patience, a stillness that is not emptiness, but rest. This is the paradox of the boreal. The harshest season is also the one that defines the forest most completely. The long winter is not a pause in the life of the forest. It is part of the life of the forest. It is the condition that made this particular kind of wilderness possible. No other forest on Earth is shaped so thoroughly by cold. No other forest holds so still for so long, and then wakes so completely when the light finally returns. The winter made the boreal what it is, and every spring, when the snow begins to melt and the first birds return to the treetops, the forest proves once again that it was worth the wait. And then the light returns. It comes back slowly at first, a little more each day. The sun climbs higher above the horizon, and the air begins to soften. In the boreal forest, this shift is not subtle. After months of cold and dark and stillness, the arrival of summer feels like a door swinging open. The whole forest responds at once. The boreal summer is short. Depending on where you are in the forest, the warm season may last only 6 to 10 weeks. In some northern reaches, the growing season is barely 2 months long. That is all the time the forest gets. And yet, what happens in those weeks is extraordinary. The sun becomes the engine of everything. During summer, the boreal forest sits so far north that daylight can stretch for 18, sometimes 20 hours a day. The sun barely sets. It grazes the horizon and rises again almost immediately. painting the sky in long golden hours of amber and rose. This is called the midnight sun, and it is one of the great gifts the far north receives in exchange for its brutal winters. The trees drink in that light. They use it to pull carbon dioxide out of the air and turn it into sugar, into wood, into growth. This process is called photosynthesis, and in the boreal summer, it runs almost without stopping. That carbon the trees absorb is ancient. It was once part of the atmosphere, floating as invisible gas above the forest. Before that, it may have been locked inside rock or dissolved in ocean water or exhaled by an animal that lived thousands of years ago. Carbon moves through the world in a great slow loop, passing through air and soil and living things across millions of years. When a spruce tree in northern Canada pulls carbon from the summer air and builds it into a new ring of wood, it is participating in a cycle that stretches back to the very beginning of life on Earth. The water the forest uses is just as old. The rain that falls on the boreal, the snowmelt that soaks into the soil each spring, that water has been cycling through the planet for billions of years. Some scientists believe that much of Earth's water arrived here long ago, carried by icy comets and asteroids that struck the young planet. Water that fell as snow on the boreal this past winter may have traveled through clouds, through rivers, through the bodies of animals, through the deep ocean, and through the ice of ancient glaciers before landing softly on a spruce branch. It has been on this planet far longer than any forest. The soil that feeds the summer growth is thin and acidic. Boreal soil is not rich like the dark loam of a temperate forest. It is pale and sandy in places, dense with partly broken down plant material called peat in others. The cold slows the work of decomposition, the process by which dead leaves and fallen trees are broken down into nutrients. So the soil stays lean. The trees have adapted to this. Spruce and fir and pine are not demanding. They ask little of the ground and take what they can get. The nitrogen in that soil, the element that living things need to build proteins and grow, was forged inside stars. Every atom of nitrogen in a boreal tree, in the moss on the forest floor, in the body of a moose grazing at the edge of a lake, was created in the nuclear furnace of a star that lived and died long before our sun existed. When that star exploded, it scattered its elements across space. Some of that material eventually gathered into clouds of gas and dust. And from those clouds, our solar system formed. The nitrogen in the Boreal Forest has been part of planets, of rock, of ancient seas, of countless living things across deep time. It arrived in this forest after a journey of billions of years. All of this, the light, the carbon, the water, the nitrogen, the thin, cold soil, comes together in the boreal summer to produce something remarkable. The forest erupts. Leaves unfurl. Flowers bloom in the understory, that low layer of plants beneath the tall trees, in brief, bright bursts of yellow and white and purple. Insects hatch by the billions. Birds arrive from thousands of miles away to nest and feed. The whole system accelerates, packing a full year's worth of growth and reproduction into a few urgent weeks. The boreal summer is not long, but it is fierce with life. Every living thing in the forest knows, in whatever way living things can know such things, that the window is narrow. And so the forest does not waste a single hour of light. And when the summer fades, when the light begins to pull back and the cold returns, what remains standing is what truly defines this forest. The trees, tall, dark, and patient beyond anything we can easily imagine. They are the bones of the boreal, and they are unlike the trees of warmer places in almost every way. The boreal forest is ruled by conifers. These are trees that carry their seeds inside cones rather than flowers. Spruce, fir, pine, and larch make up the vast majority of the forest. Walk through almost any stretch of boreal woodland, and you will find yourself surrounded by these same few species, repeated across millions of square miles. The sameness is not poverty. It is mastery. These trees have solved the problem of the North better than almost anything else alive. The most common tree in the boreal is the black spruce. It is not tall or grand by the standards of warmer forests. It grows slowly, sometimes adding less than a centimeter of height in a single year. But it is extraordinarily tough. Black spruce can survive in waterlogged soil where most trees would drown. It can grow on thin, frozen ground where nutrients are almost impossible to find. It bends under heavy snow rather than breaking. It holds its needles through temperatures that drop far below freezing. The black spruce does not thrive in spite of the north. It thrives because of it. The cold and the hardship have shaped it into something perfectly suited to this place. Those needles are part of what makes conifers so well built for cold climates. Unlike the broad, flat leaves of deciduous trees, the kind that fall every autumn, conifer needles are small, narrow, and coated in a thick, waxy layer. That wax does something important. It slows the loss of water. In winter, the ground freezes solid, and tree roots cannot pull up moisture from the soil. A broad leaf would lose water faster than the tree could replace it. The needle holds on. It keeps its moisture locked inside through the long frozen months. This is why conifers stay green all year. They do not need to drop their leaves to survive the winter. They simply wait, quiet and still, until the warmth returns. There is one striking exception to this rule. The larch, sometimes called tamarack in North America, is a conifer that does lose its needles every autumn. It turns a warm golden yellow in the fall, blazing briefly against the dark green of its neighbors, and then drops every needle to the ground. Scientists believe this strategy helps the larch survive in the very coldest and wettest parts of the boreal, where even the waxy needle cannot protect against the most extreme conditions. The larch stands bare through winter like a ghost of itself, then grows an entirely new set of needles each spring. It is one of the most cold-tolerant trees on Earth. The shape of these trees also tells a story. Most boreal conifers grow in a narrow cone shape, wide at the base and pointed at the top. That shape is not an accident. It is a response to snow. When snow falls on a broad horizontal branch, it piles up and the weight can snap the wood. But on a steeply angled branch, snow slides off before it can accumulate. The pointed shape of a spruce or fir sheds snow the same way a tent sheds rain. The tree has, over millions of years of evolution, arrived at a form that protects it from one of the most common dangers in its world, bark of boreal trees is another quiet adaptation. Spruce and fir tend to have thin bark compared to trees in warmer forests. This seems strange at first. Thicker bark might seem like better protection against the cold, but thin bark actually helps the tree in a different way. It allows the tree to shed heat more efficiently in summer and to respond quickly to temperature changes. The real insulation for boreal trees comes not from their bark, but from the snow itself, which blankets the base of every trunk through the long winter and keeps the roots from freezing solid. These trees, the black spruce, the white spruce, the balsam fir, the jack pine, the larch, are not simply plants growing in a cold place. They are the result of millions of years of pressure and response, of cold selecting for patience, of snow selecting for shape, of drought selecting for the waxy needle. Each one is a record of everything the North has thrown at living things, and each one is still standing, quiet, dark, and deeply rooted in the frozen ground below. Deeply rooted. That phrase is worth sitting with for a moment. The roots of a black spruce do not drive down into the earth the way you might imagine. They do not plunge deep like anchors reaching for bedrock. Instead, they spread wide and shallow, fanning out just beneath the surface of the soil in a broad, flat web. Most boreal tree roots stay within the top 12 to 18 inches of ground. That is roughly the depth of a shoebox. In a forest that can stand for centuries, the trees are held up by roots no deeper than your forearm is long. This is not a weakness. It is a precise answer to a very specific problem. Below that thin layer of soil, the ground in much of the boreal forest is either frozen solid or so cold and dense that roots cannot survive in it. Digging deeper would mean dying, so the trees spread sideways instead, weaving their roots together across the forest floor in a wide, interlocking mat. A stand of black spruce trees may share root space so closely that the forest floor beneath them is one continuous tangle of living wood. The trees hold each other up. A single tree in a boreal stand is rarely standing alone. The soil those roots grip is unlike the rich, dark soil you might find in a garden or a farm field. Boreal soil is thin cold and acidic. The fallen needles of spruce and fir break down very slowly in the cold. They pile up over years, forming a thick, spongy layer called duff, which is essentially a deep mat of slowly rotting organic matter. This layer can be several inches thick, soft underfoot, and dark brown, almost black. It holds water like a sponge. It insulates the soil below it, and it is home to an enormous number of small lives, fungi and bacteria, and tiny invertebrates, all working slowly in the cold to break down what the trees have shed. But here is where the scale of the Boreal Forest starts to feel truly vast. The Boreal Forest covers roughly 1.9 billion acres across the northern parts of the world. To picture that, imagine the entire lower 48 United States. Now picture that same area again, right next to it. The Boreal Forest is larger than both of those combined. It stretches across Canada, Russia, Scandinavia, and Alaska in one nearly unbroken band of green. It is the largest land-based ecosystem on Earth, and beneath every single acre of it, that thin, cold, acidic soil is doing its slow and patient work. The depth of that soil layer varies, but in many parts of the boreal, the entire living soil, the part where roots grow and fungi spread and decomposition happens, is less than 2 feet thick. 2 feet. In a forest that covers more ground than any other on the planet, the entire foundation of life is thinner than a kitchen countertop is wide. Beneath that soil, in the colder and more northern parts of the boreal, the ground transitions into permafrost, which is soil that has been frozen solid for at least 2 consecutive years, and in many places for thousands of years. Permafrost acts like a floor beneath the forest. It stops water from draining downward, which is part of why the boreal has so many bogs and wet areas pooling on the surface. The water has nowhere to go. It sits, and the forest grows around it and through it. In winter, snow adds another layer to this underground story. A deep snowpack, sometimes 3 or 4 feet thick, settles over the roots and the duff and the frozen soil. Snow is a surprisingly good insulator. The air trapped between snowflakes holds warmth the way a wool blanket does. The ground beneath a thick layer of snow can stay 10 to 20 degrees warmer than the open air above it. For roots that cannot go deeper, that blanket of snow is the difference between survival and death. So picture the Boreal Forest in January. Above the snow, temperatures may be 30 or 40 degrees below zero. The air is sharp and still. The trees stand dark and silent, but just a few inches below the surface of the snow, tucked beneath the duff and the shallow roots and the frozen earth, small organisms are still alive. Fungal threads are still slowly growing. The soil is cold, but not dead. The forest is not waiting. It is working quietly in the dark, in the cold, in the thin strip of earth between the snow above and the frozen ground below. Everything alive in the boreal has learned to live in that narrow space. Now lift your eyes above the snow. Come up from the roots and the frozen soil and the quiet dark beneath the surface. Rise up through that cold blanket of white and look at what stands above it. Because the Boreal Forest, seen from the outside, is one of the most striking sights on this planet. The trees rise straight and tall from the snow. Spruce and fir are the ones you see most often here. They are built like spires, narrow at the top and slightly wider at the base, shaped almost like the tip of a pencil pointing at the sky. This shape is not an accident. It is one of the most elegant solutions the forest has ever found. Snow is heavy. A thick layer of wet snow sitting on a wide, flat branch can snap that branch clean off. But the steep, downward sloping branches of a spruce tree shed snow the way a steep roof does. The snow slides off before it can pile up. The tree keeps its shape. It keeps its needles. It keeps working through the winter without losing a single limb to the weight of a storm. Look closely at those branches. They are covered in needles, not leaves. Each needle is small and narrow, coated in a thin, waxy layer that helps hold moisture inside. The boreal winter is cold, but it is also dry. The air holds very little water. A broad, flat leaf would lose too much moisture and freeze solid. But a needle, with its thick coat and its tiny surface, can hold on. Spruce needles can live on the tree for several years before they fall. Fir needles are similar, soft and flat, with two pale stripes running along the underside that look almost silver in the right light. The color of the boreal forest in winter is deep, dark green, almost black in the shadows. Against the white of the snow, the contrast is sharp and clean. Stands of black spruce, one of the most common trees in the boreal, have a slightly blue-gray tinge to their needles. White spruce is a brighter, cooler green. Balsam fir, which grows across much of the eastern boreal, has a rich, dense green that holds its color even in the coldest months. From above, from a plane or a satellite, the forest looks like dark velvet pressed against the snow. The bark of these trees tells its own story. Black spruce has thin, flaky bark, grayish-brown, almost scaly in texture. It peels away in small, papery pieces. White spruce bark is similar, but slightly smoother, a little more gray. The bark is not thick or dramatic the way an oak's bark might be. These trees put their energy elsewhere. They grow slowly, and their bark reflects that. Some black spruce trees in the deep boreal are only a few inches wide at the trunk, and yet they may be 80 or 100 years old. That slowness is worth sitting with for a moment. A spruce tree in the boreal might add only one ring of growth each year, and that ring might be so thin it is barely visible to the naked eye. Scientists who study tree rings, a field called dendrochronology, can read those rings like a record of every summer that tree has ever lived through. A warm summer leaves a slightly wider ring. A cold, short summer leaves a thin one. A single tree trunk holds 100 years of weather written in wood. The canopy of the boreal forest is not dense the way a tropical rainforest is. Light filters through in long, pale shafts. The trees are spaced apart enough that you can see between them, especially in stands of black spruce, which tend to grow in clusters with open patches of bog or low shrub between them. The floor beneath the trees is covered in a thick mat of moss, pale green and gray-green, soft underfoot when it is not frozen. Lichens cling to the lower branches of the trees, hanging in thin, papery sheets, or growing in small, rounded cushions directly on the bark. Some of these lichens are a pale, almost ghostly white. Others are a soft yellow-green. summer, when the snow is gone, the forest floor catches whatever light comes through the canopy. Low-growing plants like Labrador tea, with its leathery leaves and small white flowers, spread across the ground. Blueberry and crowberry grow close to the soil. The whole understory, that layer of smaller plants beneath the tall trees, stays low and compact, built for a world where the growing season is short and the light comes in at a low angle. The spruce and fir have shaped every part of this world around them. The light that reaches the ground, the snow that falls and slides and settles, the moss that grows in the shadow of their roots. They are not just trees standing in a forest. They are the architecture of the whole place. And yet, for all the quiet order of this place, something wild moves through the Boreal Forest on a regular schedule. Something that looks, at first, like pure destruction. Fire. In the Boreal, fire is not an accident. It is not a failure of the forest. It is part of how the forest breathes. Lightning strikes the dry crowns of spruce trees in late summer. A single bolt can set off a blaze that burns for weeks, moving across thousands of acres of forest. These fires can be enormous. Some boreal fires in Canada and Russia have burned areas larger than small countries. The smoke rises in tall columns visible from space. From the ground, the sound is a low, constant roar, like distant thunder that never stops. It looks like an ending. It is actually a beginning. The Boreal Forest has evolved alongside fire for thousands of years. Many of the trees and plants here are not just tolerant of fire, they depend on it. The jack pine, one of the most common trees in the North American boreal, produces cones that are sealed shut with a hard resin. That resin only melts at high temperatures. A fire passes through. The heat opens the cones, and the seeds fall onto the warm, ash-covered ground below. The ash is rich in minerals. The canopy is gone, so sunlight reaches the soil for the first time in decades. The seeds germinate quickly. A burned forest can show new green growth within a single season. Scientists call these sealed cones serotinous, meaning they are adapted to open only under specific conditions. The jack pine has essentially built fire into its reproduction. It does not wait for fire to pass. It waits for fire to arrive. Beneath the surface, the story goes even deeper. The thick mat of moss and organic material on the forest floor, built up over many decades, acts as insulation. In a low-intensity fire, this layer can protect the soil below. The roots of surviving trees stay intact. Fungi networks woven through the soil survive the burn. When the fire passes, these underground systems are still alive, ready to support whatever grows next. But in a very hot fire, the organic layer itself burns away. This exposes the mineral soil underneath, the raw, dark earth that has not seen sunlight in a very long time. That exposure is not damage. For many boreal plants, it is exactly the condition they need to germinate. Fireweed, a tall plant with bright pink-purple flowers, is often the first thing to appear after a major burn. It spreads quickly across the blackened ground, its vivid color startling against the gray and black of the burned trees. Fireweed does not just look beautiful in a burned landscape. It fixes nitrogen back into the soil, helping rebuild the chemistry that the next generation of trees will need. The standing dead trees left after a fire, called snags, become some of the most important structures in the forest. Woodpeckers move in almost immediately, drilling into the soft, insect-rich wood. Their holes are later used by owls, small ducks, and dozens of other species that need cavities to nest. A burned forest, full of gray standing trunks and open sky, holds more bird species in the years right after a fire than a dense, mature forest does. The death of the old trees creates space and structure that the living forest cannot provide. Over time, the forest rebuilds. Aspen and birch come in first, fast-growing trees that love the open light. They create a canopy that shelters the slower-growing spruce and fir seedlings beneath them. Decades pass. The spruce and fir grow tall, eventually shading out the aspen and birch. The moss returns. The lichens spread back across the bark. The floor darkens again. The forest returns to the quiet, dense, shadowed world it was before the fire. And then, eventually, lightning strikes again. The whole cycle takes roughly 70 to 200 years, depending on the region and the climate. Fire ecologists Scientists who study how fire moves through ecosystems have found that the Boreal Forest is essentially a mosaic of patches at different stages of this cycle. Some patches are old and dense. Some are mid-aged and mixed. Some are newly burned and open. Seen from above, the boreal looks like a patchwork of greens and grays and golds, each patch telling a different part of the same long story. Every part of this system connects to every other part. The fire feeds the soil. The soil feeds the seeds. The seeds become the trees. The trees build the canopy. The canopy shapes the fire when it comes again. Nothing here is wasted. Nothing is lost. It simply moves forward slowly in its own time. Tucked inside that great patchwork of trees, hidden between the spruce stands and the frozen ground, lies another world entirely. You might walk right past it without noticing. The ground softens beneath your feet. The trees thin out. The air smells different, rich and dark, like wet earth and old leaves pressed together for a very long time. You have stepped into a bog or a fen, and you are standing in one of the most important places on the planet. The Boreal Forest holds more wetlands than almost any other ecosystem on Earth. Scientists estimate that roughly 30% of the world's wetlands sit inside or alongside the boreal zone. That is an enormous amount of standing water, saturated soil, and slow-moving organic matter spread across Canada, Russia, Scandinavia, and Alaska. These wetlands are not swamps in the tropical sense. They are cold, quiet, and often covered in a thick blanket of moss. They look still. They are anything but. The most common type of boreal wetland is the peatland. A peatland forms when dead plant material, mostly moss and sedge, builds up over thousands of years in waterlogged ground. Because the ground stays so cold and wet, bacteria cannot fully break down the dead plants. The material just accumulates, layer by layer, year by year, century by century. Some peatlands in the boreal are more than 10,000 years old. They have been building since the last ice age ended and the glaciers pulled back north. That accumulated material is called peat, and it is extraordinarily dense with stored carbon. The boreal peatlands hold roughly 1/3 of all the carbon stored in the world's soils. To put that in perspective, the entire atmosphere contains about 800 gigatons of carbon. The boreal peatlands alone hold somewhere around 500 gigatons. They are, in a very real sense, the planet's largest natural carbon storage system, built one thin layer of moss at a time, over thousands of quiet years. The moss doing most of this work is called sphagnum. It is a small, soft, pale green plant that grows in dense mats across the surface of bogs. Sphagnum is remarkable. It can hold up to 20 times its own weight in water, like a living sponge stretched across the ground. It creates its own acidic environment, which slows decay even further and helps the peat keep building. Where sphagnum thrives, carbon accumulates. The two are inseparable. One tiny plant, working slowly across millions of acres, has helped shape the chemistry of the entire atmosphere. Bogs and fens are slightly different from each other. A bog gets its water only from rain and snow. It is isolated from the surrounding groundwater, which makes it very acidic and low in nutrients. A fen, on the other hand, receives water from the surrounding land and groundwater, which brings in more minerals and supports a wider range of plants. Fens can host sedges, grasses, and even small shrubs. Both are part of the same slow cycle, absorbing water, storing carbon, and quietly regulating the hydrology, the movement of water across the entire forest. These wetlands also pulse with the seasons. In spring, snowmelt fills them to the brim. The water table rises. The sphagnum swells. Frogs and insects return to the edges. Shorebirds stop here on their long migrations north, feeding in the shallow margins before continuing on. In summer, the surface dries slightly at the edges, but the deep core of the bog stays saturated. In autumn, the colors shift to deep rust and amber as the sedges die back. In winter, the whole surface freezes solid under snow, and the bog goes quiet again, waiting. This rhythm has played out for thousands of years. The wetlands breathe with the seasons just as the forest does, expanding and contracting, filling and draining, freezing and thawing. They are not separate from the forest. They are woven through it, scattered across the landscape like dark mirrors between the trees, reflecting the sky on calm mornings, steaming faintly in the cold air of early spring. The boreal wetlands also filter water. Rain falls on the forest, moves through the soil, and passes through peatlands before reaching rivers and lakes. The peat acts as a natural filter, removing sediment and absorbing excess nutrients. The clean, cold water that flows out of the boreal into rivers and eventually into the ocean begins its journey here, moving slowly through moss and peat and dark, still water. Everything in the boreal connects to everything else. The fire shapes the forest. The forest shapes the soil. The soil holds the water. The water feeds the wetlands. And the wetlands, slowly and silently, hold the carbon that keeps the whole system in balance. That clean, cold water does not stay still for long. It moves. It finds its way through the peat and the soil and the root-tangled ground, and it flows downhill, gathering into streams, then into rivers, then into the great lakes that sit like pale blue eyes across the face of the boreal forest. Water is always moving through this forest. It is one of the most water-rich places on Earth. The boreal forest holds an enormous share of the world's fresh water. Scientists estimate that this single biome, this vast belt of northern forest, contains nearly a quarter of all the fresh surface water on the planet. That includes rivers, lakes, streams, and wetlands combined. Think about that for a moment. One forest, 1/4 of all the fresh water that sits on the surface of the earth. The boreal is not just a forest. It is a water system on a scale that is hard to imagine. The lakes are everywhere. Millions of them. Many were carved out by glaciers during the last ice age, which ended roughly 10,000 years ago. Those massive sheets of ice, some more than a mile thick, scraped and gouged the rock beneath them as they moved. When the ice finally melted, it left behind hollows and basins in the land. Water filled them. Over thousands of years, forests grew up around them. Today, those glacier-carved lakes dot the boreal from Alaska to Siberia. Cold and clear and very deep in places, their bottoms still shaped by the slow work of ancient ice. The water in these lakes is cold, even in summer, the deep water stays near freezing. Cold water holds more oxygen than warm water, and that oxygen supports life. Fish like lake trout and Arctic grayling thrive in these conditions. They are built for the cold, with slow metabolisms that let them survive long winters when the lake surface freezes and light barely reaches the water below. Under the ice, life continues at a slower pace, quiet and patient, waiting for the thaw. The rivers of the Boreal are fed by snowmelt in spring. When temperatures rise and the snowpack begins to release its water, rivers swell quickly. Some overflow their banks. The surge of cold water carries sediment and nutrients downstream, depositing them along riverbanks and in floodplains. This annual flood is not a disaster. It is a renewal. The plants and animals along the river have adapted to expect it. Willows and alders grow thick along the banks, their roots holding the soil in place as the water rushes past. Salmon use these rivers. In parts of the Boreal that reach the Pacific coast, salmon swim upstream from the ocean every year to spawn, to lay their eggs in the cold, clean gravel of river beds. They travel hundreds of miles. When they die after spawning, their bodies decompose on the riverbank and in the water. Their flesh carries nutrients from the ocean deep into the forest. Bears drag salmon carcasses into the trees. Eagles drop pieces along the shore. The nutrients from those ocean fish feed the soil, and the soil feeds the trees. The forest and the ocean are connected through the bodies of fish and the cold water of rivers. The rivers also carry carbon. Water moving through peatlands picks up dissolved organic carbon, tiny particles of ancient plant matter broken down over centuries. This carbon flows downstream and eventually reaches the ocean, where it settles or is absorbed. Scientists are studying this process carefully because as the climate warms and permafrost thaws, more carbon may dissolve into rivers and flow out of the Boreal. The forest's role as a carbon store is tied directly to the behavior of its water. Even the smallest streams matter. A narrow creek threading through the spruce trees provides habitat for insects, amphibians, and the birds that feed on them. The American dipper, a small gray bird, walks along the bottom of fast-moving streams, hunting for insect larvae under the rocks. It does this in winter too, when the air is far below freezing and ice forms along the stream's edges. The water keeps moving, and the dipper keeps hunting, unbothered by the cold. All of this water, the lakes, the rivers, the creeks, the slow dark flows through peat, is part of one connected system. Rain falls on the forest. The forest holds it, filters it, and releases it slowly. The rivers carry it to the sea. The sea evaporates it back into clouds. The clouds drift north and drop snow on the forest again. The cycle turns, season after season, century after century. The Boreal Forest does not just sit beside its water. It breathes with it, the way lungs breathe with air, each one depending on the other to keep the whole living thing alive. And through all of that water, through all of those turning cycles, the animals of the Boreal Forest have found their way. Some leave when the cold comes, but many stay. And the ones that stay have found solutions to winter that feel almost impossible. The moose is the largest member of the deer family on Earth. A full-grown bull moose can weigh over 1,400 pounds. He stands taller than most horses, and yet he moves through deep snow with surprising ease, his long legs lifting high with each step, his wide hooves spreading his weight across the surface like built-in snowshoes. In winter, moose feed on the twigs and bark of willow and birch trees. They strip the bark with their teeth and swallow it. The food is tough and low in energy, but it is enough. The moose slows down, conserves heat, and waits for spring. The woodland caribou takes a different approach. Caribou travel. Their hooves change with the seasons. In summer, the soft pads grip wet ground, and in winter, the edges harden and sharpen to cut through ice and dig through snow. Caribou use their hooves like shovels, scraping away the snow to reach the lichen, a flat, crusty, slow-growing organism that clings to rocks and soil, hidden beneath. Lichen is not very nutritious, but caribou have evolved a gut that pulls every bit of energy from it. They can survive on almost nothing, drifting slowly through the forest, following the food. The snowshoe hare is smaller, faster, and one of the most important animals in the Boreal Forest. Its Its back feet are enormous compared to its body, covered in thick fur that spreads across the snow and keeps it from sinking. In summer, the hair is brown. In winter, it turns white. This color change is triggered by the shortening days of autumn, not by the cold itself. The hare's body reads the length of daylight like a clock. When the days grow short enough, the signal goes out and the white fur grows in. By the time the first snow falls, the hare is already invisible against it. The Canada lynx follows the hare almost everywhere it goes. The lynx has oversized paws, just like the hare, and for the same reason, it hunts by stealth, moving silently through the snow, barely leaving a mark. The relationship between the lynx and the hare is one of the most well-studied predator-prey cycles in all of ecology. Their populations rise and fall together in a rhythm that repeats roughly every 10 years. When hares are plentiful, lynx thrive and produce more kittens. When hares decline, lynx numbers fall too. Then the hares recover, and the whole cycle begins again. This rhythm has been tracked for over 200 years through the records of fur traders. The data shows a wave, rising and falling, rising and falling, steady as a tide. Some animals do not move through the winter at all. The black bear enters a state called torpor, a deep, slow rest where the heart rate drops and the body burns stored fat instead of food. A black bear in torpor can go 6 or 7 months without eating, drinking, or passing waste. Its body temperature drops only slightly, which is different from true hibernation in smaller animals. The bear can wake up quickly if disturbed. A mother bear gives birth to her cubs in this state, nursing them through the dark months while she sleeps. The cubs are born tiny, barely the size of a squirrel, and they grow warm and fat against their mother's sleeping body. The flying squirrel takes yet another path. It does not hibernate, and it does not migrate. Instead, groups of flying squirrels huddle together in a shared nest, pressing their small bodies close to share heat. On warmer nights, they glide out through the trees to find cached food, then return to the huddle before the cold deepens again. They are almost never seen, moving only in darkness, silent and weightless as they sail between the spruces. even beneath the snow, life continues. The subnivean zone, the thin layer of air between the snowpack and the ground, stays just above freezing, insulated by the snow above. Small mammals like voles and shrews live their entire winters in this hidden world. They tunnel through it, nest in it, and hunt each other in it. Owls above can hear them moving. A great gray owl will plunge straight through 2 feet of hard snow to catch a vole it heard from 30 feet in the air. The boreal winter is brutal, but nothing in it is wasted. Every creature that stays has found its answer, shaped by millions of years of cold. Not every creature stays. When the boreal forest begins to cool in late summer, something stirs in the trees. A restlessness, a pull. Billions of birds that spent the warm months nesting and raising young in the northern forest now prepare to leave. They will travel south, some of them thousands of miles, following ancient routes written into their bodies long before any map existed. The boreal forest is not just a home. It is the world's largest bird nursery. Scientists estimate that more than 3 billion birds breed in the boreal forest each year. That number is almost too large to hold in the mind. 3 billion. They come from wintering grounds across North, Central, and South America. They fly north in spring, nest, and raise their young through the brief summer, and then pour back south in fall. The boreal forest feeds and shelters them during the most important weeks of their lives. Many of these birds are warblers. Small, bright, quick-moving birds, barely heavier than a few paper clips. The yellow warbler, the blackpoll warbler, the Tennessee warbler. They move through the spruce and fir trees like small flames, hunting insects with extraordinary precision. A single warbler can eat hundreds of insects in a single day. During the peak of summer, when the boreal forest buzzes with mosquitoes and caterpillars and midges, these tiny birds consume vast numbers of them. They are part of the forest's great balancing act, keeping insect populations in check. The blackpoll warbler makes one of the most remarkable migrations of any songbird on Earth. In the fall, it flies from the boreal forests of Canada out over the open Atlantic Ocean. It does not stop. It cannot land on water. It flies for days without rest, sometimes covering more than 1,700 miles over open sea before reaching land again in South America. Before it leaves, the blackpoll warbler nearly doubles its body weight, storing fat as fuel. Its organs shift during migration. Its digestive system shrinks to save weight, and its flight muscles grow stronger. The bird reshapes itself for the journey. Some birds do not leave at all. The gray jay, a soft gray bird with a quiet, curious nature, stays in the Boreal Forest through the deepest winters. It survives by caching food. All through the summer and fall, the gray jay collects berries, insects, mushrooms, and scraps of meat. It hides these small parcels in the bark of trees and under clumps of lichen. The gray jay uses sticky saliva to press food into crevices where it will hold through the freeze. A single gray jay may store tens of thousands of food items in a season. It remembers where they are. Through the long winter, it retrieves them one by one. The common loon nests on the quiet lakes scattered through the Boreal Forest. Its call is one of the most haunting sounds in the natural world, a long, trembling wail that carries across still water in the early morning. Loons need clear, cold lakes to hunt. They dive deep, sometimes more than 200 feet below the surface, chasing fish with powerful legs set far back on their bodies. Those same legs, so strong underwater, make loons nearly helpless on land. They can barely walk. They build their nests right at the water's edge so they can slide in and out without struggling. The boreal chickadee is another year-round resident. It is a small bird, round and soft-looking, with a brown cap and a calm, unhurried manner. Like the gray jay, it caches food, but the chickadee does something even more remarkable. Each fall, its hippocampus, the part of the brain that handles memory and navigation, actually grows larger. New brain cells form to help it remember the thousands of locations where it has hidden seeds. In spring, when the need passes, the hippocampus shrinks again. The bird's brain changes with the seasons, just as the forest does. Shorebirds also pass through the boreal in enormous numbers. Sandpipers, dowitchers, and plovers breed in the wet meadows and bogs at the forest's northern edge. Then travel travel south along coastlines and river valleys. Some of them fly from the Canadian Boreal all the way to the southern tip of South America. They are small birds carrying enormous distances inside them. All of this movement, all of this coming and going, is woven into the life of the forest. The birds bring nutrients from distant places. They carry seeds. They control insects. They fill the summer air with sound, and then they leave, and the forest grows quiet again. The Boreal does not hold them. It simply offers what they need and lets them go. When the birds leave, the forest does not fall silent entirely. Something else moves through the trees, something low and quiet and patient. The predators of the Boreal Forest are always there, even when you cannot see them. The Canada lynx is one of the most perfectly shaped hunters on Earth. Its wide, padded paws act like natural snowshoes, spreading its weight across deep snow. A lynx can walk across a snowdrift that would swallow a deer. Its legs are long, and its back is slightly arched, giving it a crouched, ready posture even when it is simply walking. The lynx hunts almost entirely by sight and hearing. Its tufted ears catch the faintest sound, and in the Boreal Forest, it has one primary target: the snowshoe hare. The relationship between the lynx and the snowshoe hare is one of the most studied connections in all of nature. Their populations rise and fall together in a cycle that repeats roughly every 10 years. When hares are plentiful, lynx thrive and have large litters. When hare numbers crash, lynx populations follow within a year or two. Scientists have tracked this cycle using fur trade records going back more than 200 years. From the old Hudson's Bay Company ledgers that logged every pelt brought in by trappers across northern Canada. Those old records, kept for commerce, turned out to be one of the longest wildlife datasets in history. They revealed a rhythm in the forest that no one had fully understood before. The snowshoe hare itself is remarkable. In summer, its fur is brown. In winter, it turns white, matching the snow. This color change is triggered by the shortening of daylight hours in autumn, not by temperature. The hare's body reads the light and responds. When trappers and naturalists first described this transformation, Some people did not believe it. They thought different colored hairs were simply different animals. It took careful observation over many seasons to confirm that the same creature changed its coat twice a year. The wolverine is another predator that early explorers found almost impossible to believe. It is the largest land-dwelling member of the weasel family, and it is built for endurance rather than speed. A wolverine can travel 40 miles in a single day across deep snow. It has been recorded climbing sheer mountain faces and crossing frozen lakes. Early indigenous peoples and European fur traders both described it as nearly unstoppable, capable of driving bears and cougars away from a kill. Some of those accounts were dismissed as exaggeration. Modern researchers, using GPS tracking collars, have confirmed that wolverines cover distances that seem impossible for an animal of their size. The stories were true. The gray wolf moves through the boreal in packs, following the trails of moose and caribou. Wolves were once found across most of North America, but centuries of hunting and trapping reduced their range dramatically. In the Boreal Forest, they survived in greater numbers than almost anywhere else, simply because the forest was so vast and so difficult for humans to reach. Early naturalists who ventured into the northern woods brought back descriptions of wolf howls echoing across frozen lakes at night. Those sounds were often described with fear. Later researchers began to understand the howl differently. Wolves use it to locate each other, to reinforce the bonds of the pack, and to announce their presence to other packs. It is communication, not threat. The fisher is a predator that puzzled naturalists for a long time. It is a mid-sized member of the weasel family, dark and sleek, moving through the forest canopy with surprising ease. Its most remarkable behavior is hunting the North American porcupine. A porcupine is covered in thousands of sharp quills, and most animals avoid it entirely. The fisher does not. It attacks the porcupine's face repeatedly, wearing it down, then flips it over to reach the unprotected belly. Naturalists who first heard this described by indigenous hunters were skeptical. The porcupine seemed untouchable, but the fisher had found the one method that worked, and it it had been using it long before anyone from the outside world arrived to observe it. That is often how knowledge of the Boreal came together. Slowly, through the accounts of people who lived there, combined with the careful records of scientists who followed. Each predator revealed something about the forest structure. The lynx showed the power of a single prey relationship. The wolverine showed the scale of the wilderness. The wolf showed how sound carries meaning across frozen distances. The fisher showed that even the most defended creature has a weakness, and that the forest finds it in time. The predators did not just take from the forest, they shaped it. And understanding them took generations of watching. The predators shaped the forest in ways that are easy to see. But there is another group of creatures that shapes the Boreal just as powerfully, and almost no one thinks about them first. They are small. Many are invisible to the naked eye. Some live for only a few weeks. And yet, without them, the entire forest would collapse. Insects run the Boreal. That might seem like a strange thing to say about a place famous for wolves and moose and vast stretches of silent spruce. But the numbers tell the story. Scientists estimate that insects outnumber every other animal in the Boreal Forest by a margin that is almost impossible to picture. For every moose standing in a meadow, there are billions of beetles, flies, moths, and midges moving through the same trees, the same soil, the same air. They are everywhere. They are always working. Take the black fly. It is one of the most hated creatures in the Boreal, and any person who has spent a summer near a northern river will understand why. Black flies swarm in clouds so thick they can darken the air around a person's head. They bite. They are relentless. But those same black flies are a critical food source for the birds that migrate into the Boreal each spring. Warblers, swallows, and flycatchers time their arrival to match the black fly hatch. The insects emerge, the birds follow, and millions of young are raised on that protein-rich food. The thing that makes summer miserable for a hiker is what makes the forest sing with birds. Mosquitoes play a similar role. The Boreal produces more mosquitoes than almost any other place on Earth. The shallow wetlands and bogs that cover so much of the forest floor are perfect breeding grounds. A single acre of boreal wetland can produce millions of mosquito larvae in a single season. Again, this sounds like a problem. But those larvae feed fish. The fish feed bears and otters and eagles. The adult mosquitoes feed bats and birds. The mosquito is not a pest in the boreal. It is a foundation. Then there is the spruce budworm. And this is where the story gets genuinely strange. The spruce budworm is a small caterpillar, the larva of a moth that lives across the boreal. It feeds on the new growth of spruce and fir trees. In normal years, budworm populations stay low and the damage is minor. But every few decades, the population explodes. Scientists call this an outbreak. During an outbreak, budworm populations can reach billions of individuals across millions of acres. They strip the needles from trees in vast swaths of forest, and the trees die. From the air, an active budworm outbreak looks like the forest is rusting, the green turning brown in great spreading patches. For a long time, people saw this as pure destruction. Foresters fought the budworm with pesticides, trying to stop the die-off. But research over many decades revealed something unexpected. The budworm outbreaks are part of the forest's natural rhythm. The trees that die create open space. Sunlight reaches the ground. New growth rushes in. The dead wood becomes habitat for woodpeckers, which control other insects. The cycle of outbreak and recovery actually increases the diversity of the forest over time. The budworm was not breaking the forest. It was pruning it. There is also the bark beetle, a tiny insect that bores through the outer bark of trees to lay its eggs beneath. A single bark beetle is harmless, but bark beetles communicate using chemical signals called pheromones. And when a tree is stressed or weakened, the beetles recruit others. Thousands of beetles can overwhelm a single tree, cutting off the flow of water and nutrients beneath the bark. The tree dies. And again, what looks like damage turns out to serve a purpose. The dead trees fall, decay, and return their nutrients to the soil. The beetles are part of the recycling system that keeps the forest fed. Even the humble dung beetle, working silently beneath the leaf litter, moves nutrients through the soil in ways that help trees grow. Insects pollinate the shrubs and wildflowers that feed the birds and bears. Insects break down dead wood faster than almost any other force in the forest. They are the quiet workers beneath every visible thing. The Boreal teaches this lesson again and again. The creatures that seem like problems are often the ones doing the most essential work. The smallest lives carry the heaviest load, and the forest, in its long patience, has found a use for every single one of them. Beneath the insects, beneath the roots, beneath even the thin layer of soil that holds the forest up, there is another world entirely. It has no eyes. It makes no sound. It does not move in any way we can easily see. And yet, without it, the Boreal Forest would collapse within a generation. This is the world of fungi and microbes, and it runs everything. Fungi are not plants. They are not animals. They belong to their own kingdom, a vast and ancient group of living things that have been on Earth for over 1 billion years. In the Boreal Forest, fungi live mostly underground, spreading through the soil in long, thread-thin strands called hyphae. These strands are so fine that a single teaspoon of healthy forest soil can hold several miles of them, woven through the dark earth in every direction. Many of these fungi attach themselves to the roots of trees in a partnership called mycorrhizae. The word is long, but the idea is simple. The fungus wraps around a tree's roots or grows inside them, and the two share resources. The tree sends sugars down through its roots, sugars it made from sunlight during the short boreal summer. The fungus takes some of those sugars as food. In return, the fungus pulls water and minerals from the soil, things the tree's roots alone could never reach, and delivers them directly into the tree. The tree feeds the fungus. The fungus feeds the tree. Neither one could thrive without the other. Scientists estimate that up to 90% of all land plants form this kind of partnership with fungi. In the Boreal Forest, where the soil is thin and cold, and often low in nutrients, this relationship is not just helpful. It is the difference between life and death. The fungi extend the reach of every root system in the forest. A single spruce tree may be connected to dozens of fungal networks, each one stretching outward through the soil to neighboring trees. Nutrients can travel through these networks from one tree to another. A large, old tree can pass carbon and minerals to a smaller, younger tree growing in its shade. The forest does not compete the way we might imagine. It shares. Microbes play their own essential role in this underground system. Bacteria and other microscopic organisms break down dead organic matter, the fallen needles, the rotting logs, the bodies of insects and animals, into the basic minerals that plants need to grow. Without microbes, the nutrients locked inside dead things would stay locked. The cycle would stop. The forest would slowly starve. In the boreal, this decomposition process is slow. The cold temperatures keep microbial activity low for most of the year. Dead matter builds up on the forest floor, layer upon layer, sometimes for centuries. This is part of why the boreal stores so much carbon. The microbes simply cannot work fast enough in the cold to break everything down. The organic material piles up, holding carbon in place rather than releasing it into the air. But when summer comes and the soil warms, the microbes wake. They begin their work with quiet urgency. Nutrients flow. Roots absorb. Trees grow. The whole system pulses briefly with life before the cold returns and slows everything down again. There are also bacteria in the boreal soil that fix nitrogen. Nitrogen is an element that plants need to build proteins. But most plants cannot pull it directly from the air, even though the air is nearly 80% nitrogen. Certain bacteria can. They take nitrogen from the air and convert it into a form that roots can absorb. These bacteria live in the soil, on the surfaces of roots, and sometimes inside the tissues of plants themselves. They are invisible contributors to every green thing growing in the forest. The fungi, the bacteria, the microscopic organisms too small to see with the naked eye. They form the foundation beneath the foundation. The trees are impressive. The wolves and moose and bears are dramatic, but the real engine of the boreal runs silently, in the dark, in the cold, in the soil beneath your feet. Every system in the forest feeds into this one. The insects break down dead wood and return nutrients to the soil. The microbes process those nutrients further. The fungi carry them to the roots. The roots feed the trees. The trees grow tall and drop their needles and eventually fall, and the whole cycle begins again. The forest is not a collection of separate lives. It is one continuous process, passing energy and matter from one form to the next, across centuries, across miles, through the invisible threads that hold it all together. Beneath all of that invisible work, something even stranger is happening. The trees themselves are communicating, not with sound, not with movement, but through the soil, through the very fungal threads we just described. Trees send chemical signals to one another. Scientists have studied this for decades now, and the evidence is clear. A tree under attack by insects will release certain chemical compounds into the network of fungi, connecting it to its neighbors. Those neighboring trees detect the signal. They respond by producing more of their own defensive chemicals, preparing themselves before the insects even arrive. The forest is not waiting. It is listening. This was not something scientists expected to find. For a long time, trees were thought of as solitary organisms, each one competing with the others for light and water and space. That picture was not wrong, exactly. Competition does happen, but cooperation happens too, and it runs deeper than anyone imagined. A mother tree, which is simply a large, old tree at the center of a fungal network, will send extra nutrients through the soil to younger, smaller trees growing in its shade. Scientists have measured this directly. Carbon, the basic building block of all living things, moves from the roots of the old tree through the fungal threads and into the roots of the young one. The young tree receives a gift it did not ask for. The old tree gives it without any visible effort. This exchange has been happening in forests like the Boreal for millions of years. What makes this even more remarkable is how the network changes over time. A young forest is a simple network. The trees are small. The fungal threads are few. The connections are thin and new. But as the forest ages, the network grows more complex. More trees join it. More species of fungi weave themselves into the web. The older a forest becomes, the richer and more connected its underground system grows. An old-growth boreal forest, one that has never been cut, carries a network of extraordinary depth and complexity. Scientists believe these ancient networks may be more resilient, better at sharing resources, better at helping the whole forest survive stress and drought and cold. This is one reason why old forests are so difficult to replace. You can plant new trees. They will grow. But the underground network takes generations to rebuild. A young planted forest and an ancient natural forest may look similar from above. Below the surface, they are entirely different worlds. The boreal forest has been building its networks for thousands of years. Since the last great ice sheets retreated, roughly 10,000 years ago, the trees have been slowly spreading northward, establishing themselves in the cold, thin soils, weaving their roots into the ground, forming connections that now stretch across an entire continent. The forest we see today is the result of 10,000 years of quiet, patient growth. 10,000 years of trees talking to each other through the dark, and the conversation is changing. As temperatures across the boreal region rise, the forest is shifting. Trees are moving northward, following the warming edge of the climate. Species that once grew only in warmer forests to the south are appearing in places they were never seen before. The boreal is not a fixed thing. It is a moving one. It has always been moving, retreating before ice and advancing as ice melts. What is different now is the speed. The fungal networks, built for a specific range of temperature and soil conditions, are being asked to adapt faster than they have had to adapt in a very long time. Some species of fungi are more flexible than others. Some trees form partnerships with many different fungal species and can adjust as conditions change. Others depend on a narrow set of partners and are more vulnerable when those partners struggle. The forest is sorting itself out slowly across decades and centuries, finding new arrangements for a warming world. There is something quietly moving about this. The trees do not know what is happening in any way we would recognize as knowing. They have no brains, no thoughts, no awareness. And yet they respond. They signal. They share. They adjust. They They have been doing this since long before any human being walked beneath their branches. The mechanisms that allow a spruce tree to warn its neighbors of danger, or an old tree to feed a young one in the shade, evolved over hundreds of millions of years of plant life on this planet. They are ancient beyond imagining. The forest does not panic. It does not rush. It simply continues as it always has, passing its slow, quiet signals through the soil, one root to the next, one generation to the next, patient as stone. And moving through that patient, signal-filled forest, there is something large and dark and unhurried. The moose steps between the spruce trees at dusk, its broad shoulders catching the last amber light of a boreal evening. It is the largest member of the deer family on Earth. A full-grown bull moose can weigh over 1,400 pounds. Standing at the shoulder, it reaches nearly 6 feet tall. In the low golden light of a northern sunset, it looks almost prehistoric, something borrowed from a much older world. Moose are perfectly shaped for this place. Their long legs carry them through deep snow that would stop almost any other animal. Their wide, splayed hooves act like snowshoes, spreading their weight across soft ground. In summer, those same legs wade easily into the shallow lakes and wetlands scattered through the Boreal Forest. Moose are strong swimmers. They dive beneath the surface to reach aquatic plants growing on the lake bottom, holding their breath for up to 30 seconds at a time. Underwater, in the greenlit shallows of a boreal lake, a moose feeds in near silence. Their diet shapes the forest in ways that are easy to miss. A single moose eats around 40 to 60 pounds of vegetation each day in summer. They strip bark from young trees. They browse the tips of willows and birches. They pull up water plants by the roots. All of this pruning and grazing changes which plants grow, and where, and how tall. The moose does not intend to be a gardener, but that is what it is. And then there is the wolf. Wolves move through the boreal forest like shadows given weight. Their gray and white coats blend into the pale light of a snowy morning. A wolf pack in the boreal might range over hundreds of square miles, following the movement of prey through the seasons. Their paws are large and cushioned, nearly silent on packed snow. When a pack travels together, each wolf steps into the footprints of the one ahead, conserving energy across long distances. From above, a moving pack leaves a single line of tracks, as if only one animal passed. Wolves and moose have lived alongside each other in the Boreal Forest for thousands of years. The relationship between them is one of the most studied predator-prey connections in the world. On Isle Real, a large island in Lake Superior, scientists have watched wolves and moose interact for over 60 years. It is the longest continuous study of a predator-prey system anywhere on the planet. What they found was not simple. The two populations rise and fall together, linked in a slow oscillation that plays out over decades. When wolf numbers drop, moose populations grow. More moose means more browsing, more stripped bark, more pressure on the young trees. The forest changes shape. Then wolf numbers recover. Moose are kept in check, and the trees have room to breathe again. The predator does not simply reduce the prey. It changes how the prey behaves. Moose in wolf country move more, stay alert, avoid lingering too long in any one place. This constant movement spreads their impact across a wider area. The fear of the wolf is itself a force that shapes the forest. Light plays a role in all of this, quietly and constantly. The Boreal Forest in winter is a world of low angles and long shadows. The sun barely clears the horizon for months at a time. On the shortest days, there may be only 5 or 6 hours of pale gray light. This low light changes how animals move and hunt. Wolves are most active at dawn and dusk, when the light is soft and shifting, when shadows are long, and the contrast between dark trees and white snow makes movement hard to track. Moose, too, are most alert in these transitional hours. The edges of the day, when light is neither full nor absent, are when the forest holds its breath. In summer, the light swings to the opposite extreme. The boreal sky stays bright until nearly midnight. Animals that depend on darkness for cover must adjust. The long days push feeding hours later and later. The forest is lit in a way that feels almost surreal. A warm gold that stretches across the evening sky long after it should have faded. The moose and the wolf do not think about any of this. They simply live inside it. But together, moving through the light and shadow of the northern forest, they keep something in balance that no single species could maintain alone. The trees grow where they grow in part because of where a moose chose to browse and where a wolf chose to follow. The whole forest carries the shape of that ancient relationship, written quietly into every stand of spruce and birch. Beneath all of that, beneath the wolves and the moose, beneath the spruce and the birch, beneath the moss and the roots and the slow, cold soil, something vast and quiet is at work. The Boreal Forest holds carbon. It holds an enormous amount of it. And the way it does this is one of the most important stories on Earth. Carbon is the building block of life. Every living thing is made of it. When trees grow, they pull carbon dioxide out of the air and lock it inside their wood, their roots, their needles. This is how forests help regulate the air we all breathe. But the Boreal Forest does something that most forests cannot. It stores carbon not just in its trees, but in the ground itself, in deep layers of wet, cold, slowly rotting plant matter called peat. Peat forms when dead plants do not fully break down. In warm places, fallen leaves and branches decompose quickly. Bacteria and fungi eat them fast. But in the cold, wet soils of the boreal, that process slows to almost nothing. Dead moss and plant matter pile up over centuries, layer by layer, pressed down and waterlogged. The cold acts like a lid on a jar, slowing the release of carbon back into the air. Some peat deposits in the boreal are thousands of years old. They hold carbon that has been locked away since before recorded history. Scientists estimate that the Boreal Forest and its peatlands hold roughly 1/3 of all the carbon stored in land-based ecosystems on Earth. That is an extraordinary number. The trees themselves hold some of it, but the ground holds far more. The soil beneath a boreal forest can be several meters deep with accumulated organic matter, all of it quietly holding carbon that would otherwise be floating in the atmosphere. Now think about sound for a moment. The boreal is not a loud place. Wind moves through the needles with a low, steady hiss. Ice shifts and cracks in the rivers with a deep groan that carries far across the frozen landscape. In spring, meltwater runs under the snowpack with a soft, constant murmur you can hear if you press your ear close to the ground. These are the sounds of a system working, of water moving, of temperature changing, of the forest slowly breathing in and out across the seasons. The carbon cycle has its own kind of rhythm, too. In summer, the forest inhales. Trees and plants pull carbon dioxide out of the air as they grow. Instruments placed in the boreal canopy actually measure this. The concentration of carbon dioxide in the air above the forest drops slightly during the growing season as the trees take it in. Then, in autumn and winter, as decomposition slows and the trees go dormant, the numbers shift again. The forest exhales. The cycle turns. Scientists can track this like a heartbeat, a slow seasonal pulse moving through the northern latitudes. The boreal forest is so large that this pulse shows up in global measurements. Monitoring stations around the world record a slight dip in atmospheric carbon each northern summer, driven in part by the vast green engine of the boreal pulling carbon down into wood and soil. It is one of the few places on Earth where a single ecosystem is large enough to influence the chemistry of the whole atmosphere. And yet, the sounds of this process are nearly silent. There is no rumble, no crack, no call. Carbon moves invisibly, dissolved in water, locked in wood, buried in peat. The work is done in stillness. The forest does not announce what it is doing. It simply does it, the way it has for thousands of years, steady and unhurried in the cold and the dark and the long, quiet winters. There is something deeply calming about that. The idea that beneath the visible world of wolves and moose and spruce trees, there is another layer of work being done. Patient work, ancient work, the slow accumulation of carbon in peat beds that took millennia to form. The quiet chemistry of soil and cold and time. The forest does not need to be dramatic to matter. It does its most important work in silence. The boreal holds its carbon the way the night sky holds its stars. Not loudly, not with any effort you can see. Just steadily, continuously, across distances and timescales that are hard to fully grasp. And in that steadiness, in that quiet holding, it keeps something in balance for the entire planet. Something that every living thing on Earth depends on, whether they know it or not. Beneath that stillness, beneath the peat and the roots and the slow chemistry of the forest floor, there is something even older, something that has been frozen in place since the last ice age ended, roughly 10,000 years ago. It is called permafrost, and it is exactly what the name suggests. Ground that stays permanently frozen, year after year, century after century, locked in a cold that never fully lets go. The numbers behind permafrost are quiet and enormous at the same time. Permafrost covers about 25% of all the land in the northern hemisphere. That is 1/4 of the entire landmass of the planet above the equator, held in a grip of ice that does not thaw with the seasons. In some places, this frozen ground reaches down only a few feet. In others, it plunges hundreds of feet deep into the earth. In the coldest parts of Siberia, permafrost extends more than a mile straight down into the ground. A mile of frozen earth, sitting silently beneath the surface, older than any living tree. What makes permafrost so remarkable is what it holds. Frozen inside this ancient ground are the remains of plants and animals that lived and died thousands of years ago. Grasses, roots, insects, and even large animals like woolly mammoths have been found preserved inside permafrost, their bodies nearly intact after tens of thousands of years. The cold acts like a natural deep freeze, slowing decay almost completely. Time in permafrost moves at a different speed than it does anywhere else on Earth. And inside all of that frozen organic matter, there is carbon, enormous amounts of it. Scientists estimate that permafrost holds roughly 1.5 trillion tons of carbon locked inside the frozen ground. That number is almost too large to picture, but here is a way to feel its scale. The entire atmosphere of Earth currently holds about 860 billion tons of carbon. Permafrost holds nearly twice that amount, buried in the frozen dark below the Boreal Forest and the Arctic tundra. It is the largest single carbon store on land anywhere on the planet. The relationship between permafrost and the Boreal Forest is one of the most precise and delicate balances in all of Earth science. The trees of the boreal help keep the permafrost frozen. Their canopy shades the ground from summer sun. Their roots hold the soil in place. The thick layer of moss and organic matter on the forest floor acts like insulation, keeping the cold locked in below. Remove the trees and the ground warms. The permafrost begins to thaw. And when permafrost thaws, the ancient organic matter inside it begins to decay at last, releasing carbon dioxide and methane into the air. Methane is a gas that traps heat in the atmosphere about 80 times more effectively than carbon dioxide over a 20-year period. That single number carries enormous weight. It means that even a small release of methane from thawing permafrost can have an outsized effect on the warmth of the planet. The math is precise and unforgiving. The balance the boreal maintains is not approximate. It is exact. There is something almost mathematical about the way permafrost forms and holds. Water freezes at exactly 32 degrees Fahrenheit, 0 degrees Celsius. That is a fixed rule, written into the physics of water itself. Permafrost exists because temperatures in the far north stay below that line long enough and consistently enough to freeze the ground to great depths. The cold accumulates over centuries, the same way interest accumulates in a bank account. Slowly, steadily, year after year, until the balance becomes something vast. When scientists drill into permafrost to study it, they can read the layers like a history book. Each layer holds clues about the climate of the time when it formed. The pollen of ancient plants, the chemistry of old air bubbles, the remains of creatures that lived in a different world. Permafrost is an archive. It stores information about the past with the same faithfulness that it stores carbon. Everything frozen inside it is held in place, waiting. The Boreal Forest sits above this archive like a guardian. Its roots reach down into the cold. Its shade falls across the surface. Its moss and peat press down against the frozen ground, keeping the temperature just where it needs to be. The forest and the permafrost are not separate things. They are one system, each one depending on the other to stay in balance. The numbers are elegant in the way that all true things are elegant, not complicated, just precise. A fixed freezing point, a trillion tons of carbon, 10,000 years of cold. The forest above, the ice below, and between them, a balance that has held across all of recorded human history. That balance does not stay inside the forest. It reaches outward into the sky, across the oceans, and all the way around the planet. The Boreal Forest shapes the weather of the entire northern hemisphere, not as a small influence, as a major force. Think about the sheer size of it. The boreal stretches across more than 5 billion acres of land. That is roughly a third of all the forests on Earth. A system that large does not simply sit beneath the sky. It talks to the sky. It changes the sky every single day. Trees breathe. They pull carbon dioxide in through their leaves and push oxygen out. But they also release water vapor into the air. This process is called transpiration, and it works something like sweating. A single large spruce tree can release hundreds of liters of water into the atmosphere on a warm summer day. Now multiply that by hundreds of billions of trees. The Boreal Forest pumps an almost unimaginable amount of moisture into the air above it. That moisture rises, cools, and forms clouds. Those clouds produce rain and snow, not just over the forest, but far beyond it. Scientists have found that the Boreal Forest helps generate rainfall patterns across much of North America and Northern Asia. The forest is not just living under the weather. It is helping to make it. The clouds that form over the boreal do something else as well. They reflect sunlight back into space. Bright white clouds act like a mirror. They bounce the sun's energy away before it can warm the ground. This is called the albedo effect, where albedo simply means how much light a surface reflects. Snow-covered ground has a very high albedo. Dark spruce trees have a low one. They absorb heat, but the clouds those trees help create pushback against that absorption. The forest and its clouds find a middle ground, a steady, self-regulating temperature that keeps the region from swinging too far in either direction. This is what scientists mean when they call the boreal a climate engine. It does not just respond to the climate around it. It actively participates in setting that climate. It is a machine made of wood and water and cold air, running continuously, quietly, without any moving parts you could hold in your hand. The forest also affects something called the jet stream, the powerful river of wind that flows high in the atmosphere above the northern hemisphere. The jet stream steers storms. It guides cold Arctic air southward and pushes warm tropical air northward. The temperature difference between the boreal region and the warmer zones to the south helps drive the jet stream's behavior. When that temperature difference changes, the jet stream can shift. It can slow down or bend in unusual ways. Scientists are studying how changes in the boreal's temperature may already be affecting storm patterns and weather events across the entire hemisphere. The connections run deep and wide. There is something almost fragile about all of this. The conditions that make it work are precise. The boreal sits in a band of latitude where temperatures are cold enough to preserve permafrost and support slow-growing conifers, but warm enough to allow a brief summer growing season. Move that band north or south by even a few degrees of average temperature, and the system begins to shift. The trees that anchor everything in place start to struggle. The permafrost beneath them softens. The carbon stored in the soil begins to escape. The moisture the forest sends into the sky changes in volume and timing. Earth sits at a very specific distance from the sun. Not too close, not too far. Its atmosphere holds just enough heat to keep liquid water on the surface. Its tilt gives us seasons. All of these conditions have to be right at the same time for a forest like the boreal to exist at all. The boreal is not just a product of those conditions. It is one of the systems that helps maintain them. It stores carbon that would otherwise warm the planet. It generates clouds that cool the surface. It keeps the permafrost frozen, which keeps even more carbon locked away. Each piece holds the others in place. When you look at the boreal forest from above, from a satellite image taken in summer, it appears as an endless wash of deep green rolling across the top of the world. It looks still. It looks ancient and unchanging. But underneath that stillness, it is working, breathing, sending water into the sky, locking carbon into the ground, talking to the atmosphere in a language made of moisture and temperature and wind. The forest and the weather are not two separate things. They are one conversation, ongoing, unbroken, stretching across the whole wide northern sky. Long before scientists gave the Boreal Forest its name, people already knew it. They had lived inside it for thousands of years. They had learned its rhythms, its dangers, its gifts. They had built entire ways of life around the slow pulse of this cold and ancient place. Indigenous peoples across the northern world have called the Boreal home for at least 10,000 years. In North America alone, dozens of distinct nations have deep roots in this forest. The Cree, the Dene, the Ojibwe, the Innu, the Athabascan peoples of Alaska and the Yukon. In Russia and Scandinavia, the Sami people have lived alongside the taiga for just as long. These are not recent arrivals. They are part of the forest's own history. What these communities built over those thousands of years was not just survival. It was knowledge. Detailed, specific, hard-won knowledge about how the forest works, which plants heal, which waters run clean in which seasons, where the caribou move when the cold deepens, how the ice on a river sounds when it is safe to cross, and how it sounds when it is not. This kind of knowledge takes generations to gather. It cannot be learned quickly. It is passed down through stories, through practice, through time spent listening to the land. Scientists have a name for this kind of knowledge. They call it traditional ecological knowledge, or TEK. And in recent decades, researchers have begun to understand just how valuable it is. In many cases, indigenous knowledge has pointed scientists toward things they had not yet discovered on their own. Patterns in animal migration, changes in plant behavior, shifts in the timing of seasons that official weather records were too young to capture. The forest has been changing, and indigenous communities noticed those changes long before monitoring stations were set up to measure them. This is one of the open questions that researchers are still working through. How much much do we not yet know because we have not yet listened carefully enough. The Boreal Forest is enormous. It covers more land than any other forest type on Earth. No network of sensors, no fleet of satellites can observe every corner of it. But people have been walking through those corners for 10,000 years. Their observations are a kind of record. Scientists are only beginning to understand how to read it. There is another mystery here too. The relationship between indigenous land stewardship and the health of the forest itself. Studies in Canada and Russia have found that forests managed by indigenous communities often show higher levels of biodiversity. The wide variety of plant and animal life than forests managed by governments or logging companies. The reasons are not fully understood. It may be that traditional practices like controlled burning, selective harvesting, and seasonal movement across the land create conditions that help the forest stay balanced. It may be that the simple act of being present, of watching closely and responding to what you see, makes a difference. Researchers are still working to understand the connection. There is also the question of what has already been lost. Many indigenous languages in the Boreal region are endangered. Some have only a handful of fluent speakers left. And language carries knowledge in ways that translation cannot always capture. A word in Cree or Dene for a particular kind of ice or a particular behavior of a particular animal may contain layers of meaning that a scientific description cannot fully hold. When a language disappears, some of what it carried disappears with it. Scientists and linguists are working alongside indigenous communities to document these languages before that knowledge is gone. But it is slow work, and the window is narrow. What remains, even now, is remarkable. Across the boreal world, indigenous communities continue to observe, to practice, and to share what they know. They attend scientific conferences. They contribute to land management decisions. They lead their own research projects. The relationship between traditional knowledge and modern science is not a competition. It is a collaboration still finding its shape. The forest itself does not know the difference between a scientist with a measuring device and an elder who has walked the same ground for 60 winters. Both are paying attention. Both are trying to understand. And the forest, in its slow and patient way, holds the answers to questions that neither group has thought to ask yet. There is something quietly wonderful about that. A forest so large, so old, so full of life, that 10,000 years of human attention have not yet uncovered all its secrets. The Boreal keeps its mysteries gently, not hidden exactly, just waiting for the right question, asked in the right season, by someone willing to stand still and listen. Standing still and listening is something the Boreal Forest rewards deeply. The forest has its own sounds and its own silences. Both carry meaning. On a still winter morning, the Boreal can feel almost completely quiet. The snow absorbs sound. The trees stand motionless. Even the wind seems to hold its breath. But that silence is not empty. It is full of small, hidden things. The soft creak of a frozen branch. The distant tap of a woodpecker working through bark. The faint crunch of a fox placing one careful paw in front of another. These sounds carry across the cold air with surprising clarity. Sound travels differently in winter. The cold, dense air lets it move farther and sharper than it does in summer heat. In summer, the forest fills with noise. Billions of insects hum and buzz through the warm weeks. Warblers and thrushes and sparrows call from every direction. The wind moves through the spruce needles with a soft, steady hiss. Rain on a boreal lake sounds like static, low and constant and soothing. These are not random sounds. They are signals. A thrush calling from a particular tree is marking its space. A warbler singing at dawn is announcing that it survived the night. The forest communicates through sound the way it communicates through soil and root. Everything is speaking. Most of it we are only beginning to learn to hear. Scientists who study soundscapes, the full collection of sounds in a natural place, have found that healthy ecosystems have a kind of acoustic richness. Many species, many layers, many frequencies filling the air at once. A boreal forest in full summer health is acoustically complex. Each species occupies a slightly different sound frequency. The way musicians in an orchestra each play a different range of notes. When species disappear, those frequencies go quiet. Researchers can now detect early signs of ecosystem stress just by listening. A forest going silent in places it should be loud is a forest under pressure. The Boreal has known many pressures across deep time, and it has known many transformations. 12,000 years ago, where dense spruce forests now stand, there was open tundra. Glaciers had only just retreated. The trees moved north slowly over centuries, following the warming. They will move again. Scientists studying long-term climate patterns believe the Boreal Forest will shift northward as temperatures continue to rise. The southern edge of the forest, where trees meet grassland and farmland, will likely thin and retreat. The northern edge, where trees meet tundra, will likely advance. This is not new. Forests have migrated before, but the speed matters. Trees move slowly. Animals and insects that depend on specific tree species may not be able to move fast enough to keep pace. The relationships built over thousands of years between species, between predator and prey, between fungus and root, between insect and flower, take time to form. A forest that moves too fast may leave some of those relationships behind. In 1,000,000 years, the Boreal as we know it will be unrecognizable. The continents will have shifted slightly. North America and Europe will be fractionally closer together. The climate will have cycled through warm periods and cold ones many times over. Ice ages will have come and gone. The trees that exist today may have given rise to new species, shaped by pressures we cannot predict. Some species alive in the Boreal right now will be gone. Others will have evolved into forms that don't yet exist. The forest will still be there in some form. Life is persistent. It fills available space. It adapts to what the world offers. In 1,000,000,000 years, the picture changes more dramatically. The sun will be roughly 10% brighter than it is today. That extra heat will slowly begin to alter Earth's climate in ways that make the current Boreal zone unrecognizable. Scientists believe that over very long timescales, a brighter sun will eventually make Earth too warm for the kind of complex forests we see today. But 1,000,000,000 years is an almost unimaginable span of time. Life has existed on Earth for nearly 4 billion years. In that time, it has survived asteroid impacts, volcanic winters, and ice ages that covered the planet pole to pole. Whatever comes next, life will find a way to respond. For now, the boreal stands. It breathes. It holds more carbon than any other land ecosystem on Earth. It filters water for millions of people. It shelters creatures that have no other home. It holds the quiet of a winter morning and the noise of a summer afternoon. It keeps its secrets patiently, the way only very old things can. And somewhere in the deep spruce, something small and warm is listening to the silence, waiting for the right moment to make its move. The Boreal Forest has been under pressure for a long time, but the pressure it faces today is different from anything it has known before. Temperatures across the boreal zone are rising roughly twice as fast as the global average. The far north warms faster than the rest of the planet because of the way ice and snow reflect sunlight. When that ice and snow disappear, dark ground and dark water absorb more heat. That extra heat melts more ice. The cycle feeds itself. Scientists call this effect Arctic amplification, and it is already reshaping the northern world. The tree line is moving. Across much of Canada, Alaska, and Siberia, trees are pushing northward and upward into areas that were once too cold to support them. Shrubs are spreading across the tundra. Spruce seedlings are taking root in places where no spruce has grown in thousands of years. This sounds like growth. In some ways it is. But it is also a sign of a system being pushed beyond its old boundaries, moving faster than many of the animals and plants that depend on it can follow. The insects are responding too. The mountain pine beetle, a small bark beetle no bigger than a grain of rice, has expanded its range dramatically as winters grow milder. Cold winters once killed most beetle larvae before they could mature. Now, across vast stretches of British Columbia and into Alberta, the beetles have swept through millions of acres of lodgepole pine. The trees turn red, then gray. Then they stand as dry, hollow columns waiting for fire. The beetles are not invaders. They belong to this forest. But warmer winters have removed the check that once kept their numbers in balance. Fire seasons are growing longer and more intense. The boreal has always burned. Fire is part of how it renews itself, but the fires burning today are larger and more frequent than the historical record suggests they should be. In 2023, Canada experienced its worst wildfire season ever recorded. More than 45 million acres burned. The smoke drifted south across the United States and east across the Atlantic Ocean. Cities thousands of miles away turned orange. The boreal was sending a signal, written in ash and carried on the wind. When the forest burns at this scale, it releases the carbon it has stored for centuries. The peat bogs, those slow and patient keepers of ancient carbon, can burn too. Peat fires burn deep into the ground. They smolder for weeks. They release carbon that has been locked away since long before any living person was born. A forest that has spent thousands of years pulling carbon out of the air can release enormous amounts of it in a single summer. This is the pressure the boreal faces. Not one force, but many, all arriving at once. Warming temperatures, shifting precipitation, expanding insects, longer fire seasons, thawing permafrost releasing methane, a greenhouse gas far more potent than carbon dioxide over short timescales. Each force connects to the others. Each one makes the others stronger. And yet, the boreal is not fragile. It is ancient, and it is large, and it has survived things that would be unrecognizable to us. It has outlasted ice sheets a mile thick. It has regrown from bare rock. The spruce and the fir and the larch are not delicate things. They are survivors, shaped by millions of years of cold and fire and darkness. The forest holds within it a deep and quiet stubbornness. What the boreal needs more than anything is time. Time to adapt. Time for its slow cycles to find new rhythms. The problem is that the changes happening now are moving faster than the forest's natural pace. A tree that takes 100 years to mature cannot simply relocate in a decade. A bog that took 10,000 years to build cannot rebuild itself in a generation. This is where the human story and the forest's story meet. The boreal covers more than 10% of Earth's entire land surface. It holds roughly 1/3 of all the carbon stored in land-based ecosystems. What happens to it matters to every person on this planet, whether they have ever seen a spruce tree or not. The air we breathe, the water that falls as rain, the stability of the climate that makes agriculture possible. All of it is connected to the health of this vast and quiet forest at the top of the world. We are made of the same atoms as the stars that burned before our sun existed. The carbon in our bodies passed through ancient forests before it passed through us. The boreal is not separate from us. It never was. It is part of the same long, slow story. And that story is still being written. And so that story continues tonight, as it has for thousands of years. Right now, somewhere in the Boreal Forest, a spruce tree is standing in the dark. Snow rests on its branches. The air around it is cold enough to sting. The ground beneath it is frozen solid. And yet the tree is alive. Its roots hold the soil. Its needles breathe slowly. It has been doing this quietly and without pause since long before any of us were born. There is something deeply steadying about that image. A tree alone in the dark, simply enduring. The Boreal Forest has survived ice ages. It has survived volcanic eruptions that darkened the sky for years. It has survived the slow, grinding advance of glaciers that scraped the land down to bare rock, and then watched as the ice retreated and the soil slowly rebuilt itself, grain by grain, over thousands of years. The forest came back each time, not quickly, not easily, but it came back. That is what resilience looks like in the natural world. It is not dramatic. It is not loud. It is a seed falling into a crack in the rock. It is a fungus threading its way through cold soil, searching for a root to feed. It is a wolf padding silently through the snow, keeping the balance of life in motion without knowing it is doing so. The boreal does not hurry. That is one of its oldest and deepest qualities. A black spruce growing in a cold northern bog may add only a few millimeters of new wood each year. A tree the width of your wrist might be older than your grandparents. The forest measures time differently than we do. It thinks in centuries. It plans in millennia. Scientists who study tree rings Those thin circles of growth laid down one per year inside every trunk can read the history of the climate in those rings. A narrow ring means a hard year. A wide ring means a good one. The trees have been keeping this record faithfully, year after year, long before humans thought to write anything down. Some of the oldest living trees in the Boreal have rings that go back 500 years or more. Each one is a quiet archive of seasons past, and the forest holds other records too. The peat bogs of the Boreal, those dark, waterlogged places where dead plants pile up faster than they can decay, preserve ancient pollen, insects, and even the remains of animals from thousands of years ago. Scientists can drill down into a bog and pull up a core of peat that reads like a history book. Layer by layer, it tells the story of what grew here, what lived here, what the climate was doing, going back 10,000 years or more. The forest remembers things we have forgotten. Tonight, while you rest, the Boreal is doing what it has always done. Somewhere, a great gray owl is turning its wide, silent face toward a sound beneath the snow. Somewhere, a river otter is sliding under the ice of a frozen creek, moving through dark water with easy grace. Somewhere, the northern lights, those slow curtains of green and violet light caused by charged particles from the sun meeting Earth's magnetic field, are rippling across the sky above the trees, and the trees stand beneath them, indifferent and patient as they always have. The forest does not need our attention to survive, but it does need our care. The choices made in the next few decades will shape what the Boreal looks like a century from now. That is a weight worth sitting with gently before sleep. But tonight, let that weight rest. Let it be enough to simply know that the forest is there, that it is vast and old and breathing, that it is doing its quiet work in the dark, pulling carbon from the air, holding water in its soil, sheltering 10,000 species through another long winter. You are part of the same world that made those trees. The same water cycle that fills the Boreal's lakes has passed through you. The same carbon that moves through a spruce needle has moved through your lungs. The forest is not far away. It is woven into the same living system that keeps you warm and fed and breathing. And right now, that system system is holding you to. The planet is turning slowly beneath you. The stars are out. The forest is quiet. You can rest now. Subscribe for a brand new Earth topic every night. One tap, and something wonderful is waiting for you tomorrow. Sweet dreams.